Our next chapter is only really one section. And it's about the origin and history of life. So we kind of talked about evolution just as a whole, but we're going to talk about how life kind of first evolved and the evidence behind that. So we start with the Big Bang Theory. This is how we explain the universe. Kind of came into order, and all matter existed before this Big Bang in a very small space, and then through a massive expansion of space and time, not an explosion, but a massive expansion of this space. We see what we see today. It's over 13.8 billion years old, and it's still expanding till this day. And atoms started to condense and form the molecules, and these molecules bond together to form compounds, so on and so forth. And what we see in today's universe is a result of this, or kind of like just the expansion of this material. Now, a reminder: universe is 13.8 billion years old. Earth is about 4.5 billion years old, and life on Earth is about 3.8 billion years old. So before that, the Big Bang, we don't know what happened, but then after it, obviously, we get our where our time is, and we get the matter that we have from all the universe. I'm going to show you some quick videos there, but the a lot of the evidence for where life came, not actually I say a lot, but a good amount comes from this Miller-Urey experiment where they put a mixture of methane, ammonia, hydrogen, and water in a closed system, and these are elements and molecules that were found on Earth at a very early age. And this mixture was heated and electrically shocked, and this represented the very hot temperatures of Earth at that time and lightning strikes that were going on. And what happened was, for about a week, a variety of amino acids and other organic molecules were produced from these reactions, showing that amino acids and other organic molecules can form on their own. They don't need life to actually create them. We get these automatically from having uh, different mixtures of different compounds and different, we should say, like environmental factors like heat and electric. The first stage of we're going to talk about the stages of the life in the cell, but we have this mixture. This stage one is evolution of monomers. A mixture of inorganic molecules and reactions create these monomer molecules, like we just talked about, and we typically call this like the primordial soup. And what then can happen in stage two is the production of polymers from these monomers. Obviously, the polymers have many, and the monomers have one. So we're building up these monomers to build a polymer. And this is where the RNA world hypothesis comes from, where all life started using RNA because it was a much more simple molecule than DNA. And it can actually be the heritable factor, and it can act as an enzyme. So this factor, this RNA, was used as not only as a heritable factor that can be passed on from cell to cell, but it could actually work as a protein as well because it can do different functions. The third stage is the evolution of the cell, where we have protocells that develop, and it basically develops because lipids and organic molecules are going to interact in a way within water that creates this bilayer of lipids. And when the first cell started, that bilayer then could be a almost like an enclosed space for the DNA and the heritable factors, and then could split and become future cells. So this evolution of the first cell started with monomers, moved to polymers, and then finally to the cell. Let me go back. That's what the cell looks like. You can see this is actually called a protocell. These can be made in the lab, and I've actually done it before in AP biology. I don't know if we'll get to it this year, but this is a protocell that you can make on your own. The last stage, evolution of a self-replication system. This is where RNA was the template before DNA, and then DNA evolved a much more stable, just compound. DNA is much more resistant against mutations than RNA, and it can hold DNA or genetic information for much longer than RNA. So this heritable factor evolved second after RNA because it was a much more stable compound. We already talked about the RNA world hypothesis. All right, just a couple more things here. Extinction. This is when a species completely dies off due to usually environmental factors. We're seeing a rapid extinction event right now. There's been five major mass extinctions, and this decreases the biodiversity during that time greatly. You can see the end Permian is one of the worst. Almost 95% of all species died out, and it is just one of the worst. And we're not seeing numbers there yet, but we're seeing a sixth major extinction right now, much higher than we should ever really see extinction rates. But it's pretty much because humans are causing them. Last one we're going to talk about is Luca. This is the last universal common ancestor, and this last universal common ancestor must share all shares all character all characteristics share a life of life share um, characteristics with this last organism. So this first organism here, it is the first organism of all life, and we call it Luca. We're going to look at these next. These are called caladigrams, and this is specifically more like looks like a phylogenetic tree, but you can see Luca here. All life evolved from Luca, so there are a couple characteristics that all life share, and we're going to talk about that in the next chapter.